Welcome, everybody. It's my great pleasure today to introduce Ippei Obayashi, and he'll be telling us about stable volumes for persistent homology. So thanks so much, Ippei.
Okay, thank you for the introduction, and thank you for the organizer to give me a chance to talk our recent research. The topic today is the stable volumes for persistent homology. And this the result of this talk is already opened uploaded on archive, and you can download our preprint from here. Okay, third. Yeah, this is the summary of this talk. In the previous study, I proposed optimal volumes to extract geometry structures corresponding to basis pairs in persistence diagram. Yeah, and in this study, I also proposed a new idea, stable volumes, to improve the results of optimal volumes. And the concept of the stable volumes are helpful to understand the output of persistent homology. Yeah, that is persistence diagram. Okay. Before starting the contents of my presentation, I show some. I acknowledge some funding support like this. My research is supported by many funding projects. Okay. Okay, now I start my presentation. Okay, from introduction. Yeah, topological data analysis. Topological property. You already know this keyword. And topological data analysis is a data analysis method using mathematical algebra topology. And we can quantitatively characterize the shape of data using the idea of topology by using topological structures such as connected components, rings, cavities, and higher dimensional structure, topological structures. And persistent homology is one of the most important tools in topological data analysis. This persistent homology uses the idea of homology to characterize the shape of data, and persistent homology gives good descriptors for the shape of data called persistence diagrams. And the idea of persistent homology is developed rapidly in this century from mathematical theory, algorithm, software to the application to various fields such as material science and life science. So now I explain the fundamental idea of persistent homology using this simple example. Now we consider this the data of consists of 5 points. The data has two shapes. One is triangle and another is square. And to demonstrate ideal persistent homology, we consider this data. this data is a kind called this type of data is a set of points called a point cloud. This point cloud has no interesting topological structures. For example, in this data, only 5 connected there are only 5 connected components, and there are no other topological structures. But yeah, this data seems to have some interesting structures, like square and triangle. So to analyze the geometric structures from the viewpoint topology, we put disks on all points shown in this figure. For example, if in this figure there are 2 holes like this and here, and in this figure this figure has one hole here, and we can count the number of holes using the idea of homology. So yeah, in some sense, we can characterize the shape of data using this disk model, a ball model, and with homology. But yeah, here the problem is how to determine the radii of disks, because if the radii are too small, yeah, there are no holes, and the topology of this figure is the same as this figure. And if the radii are too large, like figure E, like in figure E, there are no holes. So yeah, these two structures are not so interesting from the viewpoint topology. So the problem is how to determine the radii of disks. Yeah. And the fundamental idea of Partition homology uses the process of changing radii instead of determining one radii. Yeah. For example, in this figure, in this example, some holes appears and disappear from left to right. From left to right, the radii of disks become larger from 0. And in this case, there are no holes here, and the disks becomes larger. Then 2 holes appear at the radii are A/2, where here A is is here. This is the length. This is the distance between 2 points in this figure. And in this case, 2 holes, yeah. In other words, 2 homology generators appear at here. R is A/2, and one of the holes disappears at here. At R is A/√3, and another hole disappears at here, A/√2, and we can and we call two appearance, disappearance pairs. One is this one, and another this one, are called basis pairs. And the set of all basis pairs with multiplicity are called the persistence diagrams. And we can visualize this persistence diagram using this plot. And the x-axis means bars, the first item, and the y-axis means the disappearance of the whole, called death time, called death. And the theory of persistent homology ensures the existence of basis pairs, and the theory also ensures the uniqueness of the persistence diagram. This is that's the important theory in the theory of persistent homology. And in this from this example, we can compute this persistence diagram, and the 2 points here and here correspond to the shape in this figure. These points correspond to the regular triangle here, and another point here, another basis pair correspond to the square here. Yeah, this is a fundamental idea of persistent homology. Okay, now I move to optimal volume. This is one of previous work of our new method, stable volume. So, yeah, for the analysis using persistence diagrams, we hope to identify the structure, identify the original geometric structure corresponding to each basis pair. In this example, we want to reconstruct the triangular square like this. However, this construction is not an easy task, because the representative cycle of the homology generator is not unique. For example, in this figure, there is one hole here, and in the theory of homology, the root D1, D2, and D3 have the same information of about this hole. So, from the standard theorem of homology, we cannot distinguish these loops. These 3 loops has completely the same information from the viewpoint of homology theory. But yeah, for the practical application of the homology, we want to find the best cycle from these candidates, these loops. And yeah, in this figure, in these figures, D3 in figure D looks best because it is the tightest loop surrounding the hole. So yeah, to find the best cycle, we try to find the tightest loop. Yeah, more generally, tightest homology representative. by using mathematical optimization. This is the basic idea. This kind of idea is sometimes called homology optimization. And this kind of optimization technique are developed in this decade. Shown in this, for example, many people propose and some people publish some papers about homology optimization. And my paper in 2018 proposed a method called optimal volume. Optimal volume is more adaptive to persistence homology. Now I explain the idea of optimal volumes. This figure shows the intuitive explanation of optimal volume. From left to right, we consider the increasing sequence of simplicial complex. Here, and a new homology generator is born from here. And the homology generator here dies here by filling inside the loop. And yeah, the optimal volume minimizes this internal volume, this area. Mathematically, optimal volume is defined by this optimization problem. Here, there are some new symbols like this. D is a chain complex. Oh, yeah. Or Q plus 1 dimensional, Q plus 1 dimensional chain complex, and we try to minimize the L0 norm. L0 norm means cool. Sorry, this one. Alpha k, zk, 0 equal the number of k here whose coefficient alpha k is not 0. And in this formalization, we minimize this value under the constraint of this constraint. And intuitively saying, this minimizing program minimizes this area. And the minimizer Z is called an optimal volume, and the boundary of Z is called an volume optimal cycle. In this figure, optimal volume is this area, and volume optimal cycle is this boundary. We can find this tightest area using mathematical optimization. The algorithm to compute optimal cycle is not in this slide. The idea for the first algorithm is shown. In fact, computing the such an optimization problem on D2. Let's do that is difficult. This kind of problem is shown to be NP hard, and this means that such an optimization problem is difficult, practically difficult to compute on a computer. So we need a kind of approximation. So to approximate the optimization problem, we move from Z over 2Z to R. We need to change the coefficient field from Z2 to R. And elder optimization is also a hard problem. This kind of problem is also shown to be NP hard. So we change the norm from L0 to L1. This kind of technique is a well-known approximation and often used as sparse model. And finally, the program becomes a linear program, and we can solve the problem efficiently using the efficient linear programming solver. Okay. So by using these ideas, we can efficiently compute optimal volumes. Okay, now we move to the ideal stable volume. Optimal volume and any other homology optimization technique methods are very useful to analyze the data using percent homology. But these ideas remain some problem shown in this slide. One problem is the optimal volume is not robust to noise. Another problem is that we probabilistically fail to capture minimal building blocks. ちょっとなんかそれが間違ってる。ミニマルブロック。We will see these problems in this example. In this example, when a small noise is added, and the configuration points are changed a bit, then the order of the appearance of the topological structure that changes. For example, in this case, a pentagon appears first, and next, these pentagon are divided into a triangle and squares. In this case, the result of optimal volumes are a pentagon and triangle. And on the other hand, in this case, the data is very similar to this one, but in this case, this hole appears first, and after that, another hole here appears. And in this case, and the optimal volumes are triangle and a square. So, as shown in this example, optimal volumes drastically change since the order of appearance of homogeneous changes. This means that the stability theorem, the famous theorem in this famous theorem for partial homology, does not hold for optimal volumes. And in this case, we cannot capture minimal reason blocks probabilistically. In the left example. So we want to solve the problem. And this problem is also appear in 3D space data. And this is the 3 by 3 by 3 lattice point in 3D space. And noises are added to each point. And this is the one-dimensional persistence diagram. There are some points here. And these points correspond to the small squares. And these figures show the volume optimal cycles of not 2. So 3 versus pairs. These are all of these figures, and all of these shapes are squares. This is what we expected. But in figure D, this figure shows other 2 optimal volume optimal cycles. And the shape in this figure looks somewhat curious. These shapes are not squares. This phenomenon occurs because of the same reason from the because of the same reason of the previous slide. And we practically face the problem when data has a kind of partial crystalline structures like this. Figure C shows the optimal volume of this versus pair. This figure looks somewhat curious, and this is more natural. And we also face this problem when we try to analyze atomic structure of glass. And such a result sometimes far from material scientists' intuition. This is not an artificial problem, but a real problem. One approach to the problem is the statistical approach by Benick et al. In their approach, persistence levels are computed from randomly perturbed data repeatedly, and the probability distribution is computed from the repeated results. And this figure shows the result of this method. In here, 4 points have a probability 1.0, and this point have 0.5. Therefore, these 4 points are more important. So, this idea is clever and easy to implement because we need to do is to compute the diagrams and optimal volumes repeatedly. However, to apply this method, we need to compute persistence diagrams and solve the homology optimization many times, and it represents much computation cost. Another solution in the previous study is called reconstruct shortest cycle. And this idea is implemented in Lipsler JR by Kufo. This the reconstructed shortest cycles are computed from the representative cycle in persistent homology using shortest path problem. I have no time to explain the details, but the advantage of this idea is the low computation cost because it uses the very efficient algorithm, the shortest path algorithm. But this idea has also some disadvantage. One disadvantage is we can compute only we can the one problem of the reconstruct shortest type is we can only apply the idea to one-dimensional persistence homology because we use the shortest path algorithm. And another problem is that we sometimes shortest root criterion does not give a result consistent with persistent homology structure. So now for that purpose, I propose a new idea, stable volumes, by as a result of this optimization problem. This homologization is very similar to optimal volume, but a bit different. Here. This parameter epsilon is called a noise bandwidth parameter. And R of sigma is the appearance sign or birth sign of the simplex sigma. Yeah, we can modify the optimal volumes a bit, and we can apply the idea like this. And this slide shows the formalization of optimal volumes and stable volume. This is very similar, and these two results is strongly related. This slide shows the mathematical property of stable volume. By adding the small noise to the input data, optimal volumes are changed when like this. And stable volume is a common part of all optimal volumes under small noise. And the small is determined by the noise bandwidth parameter, epsilon. In fact, this fact is only ensured when the simplicial complex is embedded in Rn. We consider ns1 and n-1 dimensional persistence diagram. However, in other cases, several volumes usually gives expected results. Yeah, I skip here. And now I show some examples of the several volume. The several volumes are already implemented in HomeCloud, and the HomeCloud is the first homology-based software developed by our research group. And this is a stable volume, and this is the optimal volume. Yeah, this result, it looks more natural. And we can apply the same data. We can apply the statistical approach to the same data. And this result is consistent with stable volume, but in some sense, it is more difficult to interpret than stable volumes. And this is an example of a reconstructed shortest cycle. And this is these figures show two reconstruct shortest cycle with another noise bandwidth parameter. The right figure shows probably expected result, but this figure shows a bit. This is a kind of not consistent. With we not consistent with the percent homology structure in the original data. This figure shows the application to more realistic data. And the data comes from the atomic configuration of amorphous silica. And this is the one-dimensional persistence diagram. And we consider this basis pair here. And this figure, the right figure, shows the optimal volume and stable volume of the basis pair. Optimal volume, the orange loop, is a bit curious ring, but in some sense, the green one is more somewhat tighter loop, and we can say that this loop is more a kind of essential part of this basis pair. Okay, now I skip here this presentation here. Now I I summarize my talk. Optimal volumes are proposed, identify the geometry structure corresponding to the basis pair. The optimal volumes and other optimizer technique are helpful to data analysis using percent homology, but optimal volumes have some drawbacks like this. The drawbacks are robustness to noise, and we sometimes fail to capture the minimal building blocks. And stable volumes improve the results by introducing a new parameter called a noise bandwidth parameter. And stable must give us more natural results than optimal volume. And we can apply the idea of stable volumes using HomeCloud. Okay, now I stop my presentation here. Thank you for your attention.
Great, thank you so much. So before we get to questions, please unmute yourself. Let's applaud for the speaker. All right, questions for Ippei?
So I have one question. So I want to ask if you compute, so the stable volume you compute for some epsilon or for all epsilon? So first of all, thanks for the nice talk. I wanted to ask you if you compute the stable volume for a small epsilon, or for a single epsilon, or for all epsilon. So you use epsilon, right? You introduce this as a parameter. Yeah. So for a single epsilon or for all epsilon? For every epsilon or for just one single epsilon, how do you compute?
Your question is about the noise bandwidth parameter. Epsilon.
Yeah.
Yeah. Your question is about the choice of epsilon.
Yeah.
For example, in this case, this is the optimal volume, and this is the stable volume for epsilon is 0.1. We can change the when change the parameter epsilon, the optimal, the stable one change of course. So your question is how to choose the parameter.
Yeah.
And this figure shows the this figure shows the epsilon versus stable volume size. By changing the epsilon, the volume becomes smaller. And when between 0.1 to 0.25, the size does not change. It means that the stable volume is stable in this area. So in this example, we choose this parameter.
Okay, got it. Thanks.
To choose the parameter, we need to change epsilon and we need to compute stable volumes for many epsilon.
Okay, thank you.
To find a good parameter.
Thanks. That answers my question. Thanks.
More questions?
Can I? Yes, I have a question. You hear me? Robert Adler.
Yes, please go ahead.
Could you go back to the slide? I think it was the the second last slide or the third last slide. Anyway, the last example that you did.
Last example.
Must be slide, probably slide 30, 31.
This one?
Keep going.
Hmm?
A bit more.
Hmm?
Yes. No. Okay, go back one.
Back one?
I think the one with the
32.
green and the orange loops.
I guess it's 32. No, I guess it's 31.
And this one?
One more. Yeah, that's it. Okay. So there's the green cycle, and okay, so now I think I see it better. The orange or red or orange cycles, that's not one big cycle, right? That's just a lot of cycles. So you have a lot of cycles, each one around about the same length as the green cycle. Is that correct?
Mm-hmm.
Yes. So there are like 3 or 4 orange cycles. The picture's in R3?
Yeah, this is
Okay. So
R3,
it's
in R3.
Okay, so there's one green cycle and there is one orange cycle.
Yes, that's right.
Okay, so then I do not understand why the orange cycle was ever picked as a minimal cycle, even without volume considerations, since it is so much longer than the green cycle.
Yeah. Yeah. Probably, and this figure shows the reason why. Yeah, the appearance, because in fact, in the amorphous, the distance between the 2 points are almost same, because this distance corresponds to the kind of chemical bond. And for probably we consider this kind of a bit complex example. Yeah, in this case.
Okay, now I think I am. Okay, I understand.
Probably
It's
to
Henry's comment. Yeah, because it's in 3. It's in.
But
it's very much because it's
a
2-dimensional projection of a 3-dimensional picture.
Yeah.
So that small cycle could go very far back in depth. Yeah. Okay. Sorry. Okay. Thank you. Yeah. I need a 3-dimensional iPad.
Yeah.
Yeah. Thank you.
Or questions?
So if there's time, I have one more question. So I wanted to ask, so you said that the problem as naturally for, I was a bit late to the, sorry, I was a bit late to the talk. So you said that one of the, your first formulation was NP hard, and then you had something else that, so is it like a relaxation, or you solved some kind of linear program, right? So your original formulation was NP hard, right? Can you please tell me what your original formulation was? Yeah, maybe it was the first few slides.
This one?
Yeah, Yeah, maybe even before that. Earlier.
Yeah.
In the early slides.
Earlier.
Yeah. Maybe even like towards the start of the talk.
I think the definition of optimal volume.
Definition of optimal volume.
Can you please go to the start of the talk, like in the first couple of 3 or 4 slides, because there's something I missed. I joined the meeting late, so I missed something. So yeah, well, okay. So what is Z0? It's okay. So this is the problem you're solving. It's the I see.
We solve this optimization problem using some approximation.
I see. Okay. And so this is the number of simplices that are, I don't really understand. So this is the
number of simplices. Yes, that's right.
Okay. Okay, thanks. I understand better now.
Ippei, I have a question related to this. So in general, the L1 problem does not give the same answer as the L0 problem, right? But are there subcases where it's known that the L1 answer gives the same answer as the L0 problem?
Probably yes. Yeah. In fact, I'm not sure the detail, but some famous mathematician proved that showed that fact. I'm not sure who proved that fact. Yeah.
Okay. Right, like Donahoe has studied this, showing when does L0, give you the L. When does L1 give you the L0 answer on sparse problems? But but I don't know if it. It reminds me a little bit of this. There's this paper, TU modularity paper by Tamal Day and Bala Krishnamurthy and Anil Hirani. So they consider a related problem where in some cases the L1 relaxation solves the L0 problem. So that's just one reason why I ask. Maybe it happens sometimes here, which would be interesting if so.
I don't know. Yeah. So yeah, that's a good information for me.
So maybe we have time for one last question during the recorded portion. Any last questions? Well, if not, thanks so much, Ippei, for the fantastic talk, and we'll stop the recording here.